So Nat's an awesome guy. Colby and I actually work with him on benchmarking, which I believe we'll be touching on a little bit, I assume. So, right, Colby? Great. So, yeah. So we all work together on kind of trying to build a benchmark that allows you to fairly compare different kinds of embedded systems already. At this point, while we have been using the Arduino board, there are many other boards. For instance, Danilo talked about the STM Cube platform. There's a whole slew of different AI hardware coming. So if all of this stuff is coming out, how do you kind of make sense of it? That's a critical aspect. So Nat has been instrumental in that effort in terms of building the benchmark, which I think we'll get into. Then Nat's actually also quite instrumental in the TensorFlow-like micro, the code base itself, and contributing. I think Pete can actually get much more into that. Pete, turn it over to you.
Yeah, I mean, Nat is really a very core member of the team. He's doing the TinyMLPerf stuff almost as like a side gig in between all of the other essential stuff he's been doing, especially around speech. And he's implemented a lot of the core stuff that we've been doing around speech recognition that's been shipping actually on devices. He's also been doing a whole bunch of optimizations. So he's really been down at the the intrinsic and the assembler level on a lot of these different devices. So he's really got a great understanding of the whole stack. He's been doing a bunch of model training. He's been doing ML Perf profiling. He's actually been going in and like optimizing all of the sort of inner loops as well based on that information. So I think he's really got a fantastic perspective on all of the different aspects of performance. So I'm really looking forward to seeing his talk.
Awesome. And when you all read the TensorFlow-like micro paper, all that performance evaluation and things, Nat kind of got us all the performance data that was there. So feel free to ask him questions about things if they're still lingering in your head. One of the other sides of the profiling thing is also about memory. So Nick actually was, he's the other person who's also on the team kind of who does a lot of that profiling stuff, and Nat knows a lot about just overall system performance. So feel free to ask him questions. With that, I'm going to turn it over to you, Nat and Colby.
Cool. Should I share my screen?
Yeah.
Yeah, go ahead.
All right. Cool. Yeah. Let's go back to the beginning. Thanks for the intro. My name is Nat Jeffries. I joined the team, at TensorFlow Micro about a year and a half ago, and actually, I'm a lot closer, I think, to kind of the stage in my career. I'm kind of early on in my career, so I'm a lot closer to you guys in the class. My background was actually originally in embedded systems. So I took kind of the non-ML path to doing ML. And it just shows that you can kind of take a bunch of different approaches to getting into TinyML. Whether or not you have a background in machine learning or a background in embedded systems, there's a lot to learn for all of us. The other thing is, please do interrupt at any point if you have any questions or I can clarify anything. So today I'm going to talk about sort of the general motivations about why do we do benchmarking, what is benchmarking, what is profiling, how do we approach these, what does it mean to have a useful benchmark versus one that doesn't meet its requirements, and what kind of what is the purpose of profiling for digging into the application you're trying to run, and how can you use them together to optimize for a given platform or for a given task. And then I'm going to go over kind of the workflow. So this is how you use them together, as well as an example on TF Micro for how do we do benchmarking on TF Micro specifically, and then how do we do profiling to improve our benchmark results, along with some results that we've already gotten in the paper that I assume you've already read for Pete's talk. So benchmarks as a whole are basically a way to measure an entire application. So that means for a given task, whether that's image processing or audio processing, you want to know, you say you have a set of requirements, you need to process 1 frame a second, 10 frames a second. something like that, or audio coming in at 16 kilohertz. You want to be able to make sure that your model that you're going to be running alongside this, audio processing is going to be able to keep up with the stream coming in. And it can be hard to know this without having a representative benchmark that gives you numbers and gives you clear results. So you can know sort of in your optimization process where you stand compared with the requirements you have. And then profiling is once you have a benchmark and you've gotten the results, profiling is a way to dig into the specific task and break it down into key components, and then compare these key components to figure out where your bottlenecks are and what you need to optimize, basically. And you need to have both in order to create an efficient application. So a useful benchmark, obviously, your task is to figure out how long it takes to run something. And hopefully that something is a useful application. And so it means that in order to have it be useful, you need to make it easy to reproduce. So that means every time you run the benchmark, it produces kind of similar or identical results. And also, you want it to produce a meaningful result. And what that means is some metric, whether it's the number of clock cycles it takes to run your task, or if it's a number of seconds it takes, it needs to be clear and needs to be comparable between applications. Also, it needs to be representative of a real-world task. So there are lots of examples of benchmarks that seem great, when you hear about it, but they don't actually properly represent a real-world task. And I'll be talking about that on the next slide a little bit. And then the last thing is to make it easy to verify. And this is, when you're coming up with a benchmark, you want to make sure that if somebody says, hey, I got this great result, that result is actually, they've done it properly. And this doesn't necessarily mean that people are out there always to try to cheat, but a lot of times you can have benchmarks that if they don't properly represent something that's in the real world, it's very easy to unintentionally cheat. Your compiler can do things that it wouldn't be able to do in a real application, for example. And so a good example of a benchmark that fell short, is the Drystone benchmark. And this is primarily because it's actually not representative of real world data and real world use cases. It's a 1980s benchmark designed to benchmark a lot of string utilities and string manipulation. And it seems fine if you look at it just on the surface level, but all the strings that it's operating on are aligned to the same boundaries in memory, and they're all of the same length. And what that means is a smart compiler can look and actually change out the instructions it uses to use sort of more efficient aligned instructions instead of the instructions that would have to use in a real application where strings are not aligned and they're varying lengths. And so unintentionally, this benchmark was actually kind of easy to cheat without meaning to. And what that means is it often overstated performance by over 30%, which is a big problem if you think about it. If you've run this benchmark and you have an application and you think, OK, I'm ready to go, we're good to go, and you're still 30% short of your performance requirements, that can cause serious issues down the road. So once you've run a benchmark and you have this number or the number of cycles, or you can compare it against your requirements for the application, you then want to basically take that number and know what to do with it. And typically that is by comparing it against some requirements and digging into why that benchmark performs the way it does. And most often, I think you're going to be probably doing some benchmarking in the coming days and weeks. You're going to find that you almost never meet the requirements that the performance requirements you want the first time you run the benchmark. And so it's useful to know that the benchmark is really just it sets the goalpost. So you know where you are and you know where you're headed for, but you don't really know why. And that's why we get into profiling in order to sort of dig deeper into the application. So profiling is a way to break down that application into chunks. And at least for machine learning tasks, this typically looks like breaking it down for each operator in the graph, for example, and knowing how long it takes to run each operator. And once you've done that, you can actually you can dig deeper and figure out which operators are important and which operators are bottlenecks, and then direct your optimization efforts properly. And this is a really essential part of optimizing for a particular neural network, because if you're optimizing something that takes a very small amount of the overall runtime, you're not going to actually see major improvements to your overall benchmark. And so this is actually speaking to something, many of you have probably seen this already, but Amdahl's law is this idea. It kind of is a mathematical representation of that idea of directing your effort properly. And this is, isn't necessarily clear what this does by just looking at it, but all it's saying is if you can optimize some portion of a program and speed it up by some, n times, you're going to be able to achieve some overall speed up, and that it's related to both the fraction of the program you can speed up and also the speed up you can achieve. So just plugging some numbers into this, you can see that if you optimize 1% of the program by 100 times, that's huge optimization, and probably that's a lot of effort to do for that 1% of the program. You're only going to achieve, at most a 1% speed up. But if you optimize 50% of a program by 1.1 times, so that's like a 10% speed up, overall you're going to see a 4.7% speed up. So it just gives you a sense of how important it is to make sure you direct your efforts in kind of in a smart and in a measured way by using profiling to do so. So next I'm going to go over some typical optimization techniques. These are things that I've done on TFLite Micro, and they're techniques that I've seen a lot of our chip vendor partners do for us for some of our kernels. Overall, basically, there are a few key things that you can think about. When inevitably you run your benchmark and it doesn't quite meet the requirements you're looking for, probably the first thing to look at is thinking about quantization and reducing the integer depth of your the weights in your graph and the calculations that happen in there. And that's a TFLite feature, and I think probably Pete talked about that in his talk earlier. The next thing is going to be loop optimizations. So these are typically these are more sort of the typical computer science, computer science 101 optimizations, where it's how do you take some work out of the inner loop, and how do you optimize your memory accesses, and how do you, that type of thing that I think many of you have probably already seen. But it's important to remember those optimizations are still useful. And a lot of times, actually, what I found is I've gotten the most immediate benefits from just looking through the code base and figuring out where we can improve using these like loop optimizations. Next, I'm going to talk about hardware and toolchain features. So that's going to be hardware-specific features and ways to use your compiler better in order to better compile for the exact requirements of your platform, and also how to get the most out of that compiler and how to choose the right compiler also for the task you're trying to do. And then finally, different hardware often has specialized instructions and ways to perform an operation on multiple pieces of data at the same time, or perform extremely optimized, basically optimized computation. And this is typically on a per chip basis. And you have to recognize, depending on the hardware you have, a lot of these will be available both in the form of instructions if you want to write assembly, but also optimized libraries. So the first, I'm dig a little bit deeper into quantization. I think you've already probably talked about this, so I won't dive too deeply into this, but this is just the overall quantization scheme. And what this is doing is it's breaking down, you have tons and tons of possible floating point values, but in your graph, those values typically fall in a certain range. And so you can quantize it down into buckets and stick those into an 8-bit integer. And that's the typical quantization scheme we use in TFLite Micro is signed 8-bit integers. And what this means is you can actually do integer math instead of doing floating point math, which can be faster on a lot of embedded platforms. But also, it means that you have access to a bunch of optimized libraries a lot of times. And so even if you don't see an immediate speed up, often what I've seen is the reference kernel version of a model doesn't get a lot faster when you quantize to 8 bits, but it kind of unlocks the door to a ton more optimizations down the road. And you can also use some of the optimized kernels that we and our hardware vendors provide to do much better. Also, it's worth noting that quantization reduces the model size. And while this doesn't typically improve the runtime performance, it can improve memory performance. It can mean they use less memory. And also on a lot of chips, if you use less flash memory or less program memory and less runtime memory, the chip can actually turn off some of the memory, some of its hardware, and save power. So there are some side benefits you might not think about, but if you do have kind of strict power requirements for a given task, quantization is actually a good first step. The next kind of, again, this is sort of the computer science 101 optimization, but basically considering.
Can I ask you, sorry,
yeah.
Question?
So, yeah, go ahead.
So in the quantization scheme, right? So does TFLite use symmetric or asymmetric quantization?
Both. So TFLite uses symmetric quantization for the weights, and this is an optimization basically to avoid having to add a bias or add a 0 point to every weight. But for most things, for most activation tensors through the graph, it uses asymmetric quantization.
I see.
Yeah.
Sorry, for the student's sake, maybe it would be helpful if you just briefly just said what's the difference between symmetric or asymmetric.
Yeah, absolutely. So when you quantize down from floating point to assigned integer, for example, in order to properly represent that, you have some floating point range. A symmetric quantization scheme assumes that the maximum floating point value you want to represent is going to be the same as the minimum. And what that means is your assigned 8-bit integer, you can just multiply that by some factor in order to get your floating point values. Whereas asymmetric says you've got this overall range, and you're allowed to shift this window around 0. So you have this, you multiply by some factor to get back to floating point, but then also you add some fixed value. This is the idea of a 0 point. And it just means symmetric quantization is going to be simpler because you don't have to add a 0 point at any point, but it's going to less accurately represent, you're going to often lose about half of your possible values just because a lot of operations only if you look at the floating point values, they're going to only be positive, between 0 and some value. And so you're going to lose kind of half of your range by doing that. Does that make overall sense?
Yeah. Yeah, it's important for people to definitely know that because it does come up quite a bit in quantization. And I know we didn't necessarily poke too much into quantization, but it's something that's pretty important to know.
Yeah, and yeah, the reason that we do use asymmetric quantization is for the reason, it adds some complexity to the code, but you basically get in a lot of cases twice the bit depth, if you think, or sorry, an extra bit, twice the range that you can represent. And so it's very valuable, especially with graphs that have like ReLU activations. Those will clamp the minimum value to 0. And so having asymmetric quantization, it allows for some optimizations as well. But basically, if your range is from 0 to some maximum floating point value, you really do want asymmetric quantization because you can represent that full range from -128 to 127 in int8 instead of having to only represent half. So yeah, to get back to some optimizations you can look for. Typically, this is just sort of the computer sciencey optimization you think about, where it's you want to remove work from the inner loop, and also, especially on embedded systems, it's worth noting that memory accesses are frequently more expensive than just regular arithmetic operations. And so if you look on the left here, it looks pretty normal. This is just summing all the rows in a 2-dimensional input, and it looks fine. But this memory access, this output, updating this output in memory is actually going to be far more expensive than accumulating it to a local variable. And also computing I times W in the inner loop is unnecessary because you know what I times W is by the time you've reset. You know that in the outer loop. So on the right, this is just a super basic example, but you can have a sum that a local variable you're accumulating into, and you can pre-compute I times W here in order to reduce. This probably would see a many times speed up in a real world embedded system, just because you're accumulating into registers as opposed to into memory. And for people who've done computer architecture, that's probably a lot more of a familiar concept. But just note that accumulating into local variables is often much faster, and avoiding extra work is really important. And I've seen, it seems super basic here, but I've seen across TFLite Micro and across some of the optimizations that I've worked on, this is kind of the first pass where you can get often, 10+% improvement without doing a ton of extra work. And if anything, it's kind of cleaning up the code in a lot of places. So just keep in mind, this can be incredibly powerful, even if it does seem pretty basic. So the next thing you can think about is enabling kind of the special features of your platform. So that's going to be things like hardware floating point, if you are doing floating point operations, or cache control. These types of things are typically configured during setup. And so if you have a platform, a lot of times there'll be some code that is either provided for you or that you write in order to bring everything up, bring up the clock, bring up the board, bring up the communication, all that. Make sure that when you're doing this, you're enabling the features that are going to help you run your model quickly and efficiently. And things like hardware floating point can make a huge difference for a lot of models. And same thing with cache control. Just make sure that you explore this, especially if you have a benchmark that's not quite meeting the requirements you were looking for. This can get you massive returns in terms of your work to speed up. And then the next thing to consider is compiler optimizations. And this is somewhat related to the first 2 points. This can be as simple as enabling like -03 in GCC, but it can be also each compiler toolchain has a lot of options to do kind of sophisticated things for you. And so it's worth looking into, for your specific platform, what options you can enable in order to enable chip features and enable the right kind of floating point, things like that, in order to make your application faster. And then the final thing about compilers is to note that not all compilers are created equal for a given platform. And this sort of seems unintuitive at first, but a lot of times a chip vendor ships a particular version of a compiler with their hardware. And the reason they do this is that, for example, ARM has ARM Clang. And they ship this with their ARM platforms because this compiler really deeply understands the architecture, and it can do a much better job of optimizing, even if it's got the same input code compared with just like regular GCC. It can do a much better job because it understands exactly how expensive each operation is on that ARM platform. And also it knows about all the special instructions and special things it can do to kind of automatically get you some of these speedups. And so we've seen that some like 50% speedups before by just changing the compiler toolchain and the options. And so it's important to recognize that this is something, it's kind of a meta decision around your code. How do you compile it? But this is really, really important. And so you shouldn't forget. And then the last thing is you can increase the clock speed. So say you have an application that's running too slowly and it's getting behind the input. This is an option, but make sure you know how much you're increasing the power, especially if this is going to be a battery-powered device or something like that with some power requirements. Increasing the clock speed by a factor of 2 doesn't usually increase the power by only a factor of 2. Usually it's at least 4 times. So it's basically it's polynomial increase. So it's typically the clock speed ratio squared. And this is for a variety of reasons in hardware that I won't get into, but do note that increasing the clock speed can often have a much greater effect on overall power consumption than you'd expect. So this is kind of a last resort, and it can be good for testing and validating a model. But you probably don't want to release, if at all possible, you don't want to sort of release a project with a highly increased clock speed. So another way to optimize is to use special instructions that are present on different hardware platforms. And these are typically in the form of SIMD instructions. And what that means is single instruction, multiple data. And again, the sort of computer architecture people will be very familiar with this idea. But the overall concept here is that you bring in, the instruction takes multiple elements in. It can be 2, 4, 8 elements in. and it performs the same, arithmetic operations on those and produces 2, 4, or 8 elements out. And this can be massively powerful, especially on these embedded specialized devices, because instead of doing, you'll basically double the amount of work you can do in the same number of clock cycles, or quadruple, or 8 times. And you can go and muck around with assembly and really digging into this, or a lot of times hardware vendors provide libraries that are optimized for you in order to do some of these things. So some examples would be like SymSysNN for ARM, which I know you recently had a talk from somebody from ARM about this. And this is just a nice wrapper around these very chip-specific or architecture-specific optimizations, where it gives you, SymSysNN in particular gives you sort of whole neural network or typical neural network tasks. But a lot of the libraries are going to provide something like matrix multiplication or dot product or things like that, where you can compose an operator out of these relatively easily. And then these 3 are just examples of some of the types of optimizations we've explored and we've done, and some of them are ongoing efforts as well. But also note that we've done a lot of this work already on the TFLite micro side, and specifying optimized kernel dir during your build is going to basically enable the make process to include the optimized kernels that we've already worked with chip vendors to produce. And this could be things like SymSysNN kernels that use this ARM hardware much better. And you kind of, just by including one additional flag, you can go and get a lot of these optimizations basically for free. So do note that this is kind of the easiest first step, is just to enable optimization and to specify your target and the optimized kernel directory. So when you do benchmarking and you do optimization and you do this whole end-to-end process, it's worth knowing kind of what you can expect to see, or how much you can hope to optimize a given task. And you can look on the right for kind of the extreme example, which is the Extensa Hi-Fi Mini DSP. This is a very specialized piece of hardware, and you can see that for the Google Hot Word task, we were able to speed it up by more than 10 times. And this is actually 10 times, already having done some good optimization before. So it's a massive difference. And if you look at the visual wake words, it's a similar like 8 times speed up. But if you look on the left, you can also see that a more general purpose chip, like the SparkFun Edge, which has a Cortex M4 processor, you're going to see some speed up, but it's not going to be as massive. So you won't see orders of magnitude speed up typically, but you can have some small factor speed up. And this is just because that chip is very capable of running reference kernels and running, it has a floating point unit. It has a way to do a lot of these operations pretty efficiently out of the box. So these are kind of this is kind of the range of optimizations you can expect to see for your task, depending on the kind of hardware you choose. It also tells you that if you do run a benchmark and you're using a specialized piece of hardware and it's 10 times too slow, to not be overly concerned and to not just give up, because you can get a lot out of these very specialized chips. So overall, the workflow that you're going to take, as in the upcoming days and weeks when you're optimizing your application, is typically going to be around this profiling, followed by identifying bottlenecks, then optimizing, and then benchmarking to compare against your requirements. And so it's always important, as I mentioned before, to make sure you keep profiling and keep benchmarking in order to really direct your effort in the most effective way possible. And just keep this in mind and keep this workflow in mind when you are going about doing these optimization tasks. Next, I'm gonna dig into a little bit about how we do benchmarking on TFLite Micro and kind of how we design these benchmarks to accomplish some of the goals that I mentioned earlier, to make a sort of general purpose benchmark to run TFLite Micro models with our framework. And this is just a very stripped down kind of basic version of a benchmark. It's kind of distilled it down into the key components. And really all you have to have for a benchmark is some model and some memory, some tensor arena, and an op resolver, and then a benchmark runner. And this is just a nice wrapper for the micro interpreter and all the other kind of error reporter and other key classes in TFLite Micro. This just allows you to run the benchmark really easily without having to worry too much about what's happening under the hood. And you can, the real sort of important part about benchmarks are these last three lines. The TFLite Micro benchmarks begin and end, along with the TFLite Micro benchmark macro. And all these do is it creates a main loop for you, and it will put timing code before whatever benchmark you specify, and report after that benchmark is done running. It'll report how long it took to run. And so you can declare as many benchmarks as you want. And that can be something like running on different types of input, or it can be running the model a different number of times, something like that, in order to just get a sense of various kinds of use cases and how long it takes to do each thing. Another thing that I typically end up doing is having a benchmark for the setup. So how long it takes to initialize the model and to run the first iteration, because that's typically a lot more expensive compared with running the model in subsequent times. So it's just worth noting that can help you get a sense of kind of how the model performs. And so this is a typical result you might see for that code that I showed you before. This is using a serial console. It depends. Each platform's different, but it should print out something like this, where it tells you how many clock cycles it took, and then approximately how many milliseconds that is. And so, for example, here, if we wanted to operate at 100 hertz, say, so 100 times a second, you could tell that you'd be off. Well, you'd actually be fine because you're 3 times faster than you need to be. But you can use this to kind of get a sense of how this application performs as a whole. Next, when you're digging into the application and you want to know how each operator performs, it's actually relatively simple with TFLite Micro to do this as well. And the way you do that is by creating a micro profiler and just passing in an error reporter, and then giving that micro profiler to the micro interpreter you're using. And so I did this in the Hello World test, and it was, it's only about 3 lines of code added. And make sure you build with debug mode. So that's going to be release type equals debug, or build type equals debug, because in order to, this is sort of a bit of a tangent, but in order to make sure that we don't include a bunch of extra profiling and benchmarking and debug code during, for our internal and external sort of products, where we want it every cycle matters. We have some if defs that will pull that out. And so if you build with a release type, you're actually not going to get your benchmarking, which is by design, but it's worth just make sure that you use a debug mode build when you do profiling. And what this is going to do in the micro interpreter itself, when you run the model, it checks if there's a profiler enabled. And if there is, it's actually going to give you a result for every single operator as it loops through the operators in the graph. And it'll give you a cycle count for each one. And this is actually really useful. If you look on the right, you can see this is for the Hello World test, but in a broader sense, kind of how long it takes to run each operator. And here you can see that, for example, if we were going to optimize this, you'd probably want to look at fully connected as the main operator to sort of dig into and to optimize, because that's using the majority of the cycles. And so this is, you can see how this kind of helps you identify expensive operators and optimize them. It's also worth noting that, for Hello World, this is a really small model, and there aren't actually that many cycles being consumed in fully connected. So it might be tough to optimize this. And it might be worth recognizing that sometimes the neural network you're running is not the bottleneck, right? And so for a model as simple as this, most often your pre-processing is going to be also very worth benchmarking and make sure that the pre-processing is not taking more time than the model itself. And just to keep in mind that this sort of the idea of Amdahl's law and the idea of optimizing what matters extends beyond just the neural network and the neural network engine, but also the entire application you're writing, especially when it comes to simpler models. And once you've done that, and once you've identified kind of the expensive operators, the next step is to look, for example, in that last one, fully connected, but especially for a bigger model, to look into the operators that are taking the majority of the cycles, and to break them down and to profile each section in the operator. And the reason we did included the profiler where we did is because it's part of the context structure, which is a general purpose TFLite structure, which includes a lot of helpful classes and various utilities to do things like error reporting and profiling in this case. And so you can actually use this context profiler to create, this is a scope profile class, but there are various ways to do this in TFLite and to measure each stage of the operator and to get a sense of how long each stage takes, so you can further redirect your efforts. And in this case, an output might look like something like this, where you'd probably want to be first approaching that first stage because it seems to be almost half the total cycles, right? Maybe a little bit more. And then maybe look at the second stage and look at if you can optimize the bias. But keep running this and keep digging in and making sure that you're still optimizing things that matter the most. And then I think I'm gonna pass this off to Colby for a short discussion about TinyMLPerf and the overall organization there. So thank you.
Thanks, Nat. Yeah, that was super awesome. I think just like before I jump into this, I'd just like to sort of echo what Nat said, and just for TinyML, like profiling especially is kind of not an optional stage, as it is in maybe some other fields where you can sort of get away with non-optimized performance and code and whatnot, especially for like size reasons. I think some of you that have final projects that are ambitious are going to need to think about a lot of these things, especially, I mean, quantization is like a core thing, but some of this other stuff too, to get sort of realistic performance.
Anybody else? I'm happy to answer some questions now. I can also, once Colby's done talking about TinyMLPerf, we can, field questions as well.
Cool. Yeah. So I think after this we'll probably have a bunch of questions. Yeah. So I'm just going to quickly go over TinyMLPerf, which is sort of an effort that VJ, Nat, and I have been working on along with a lot of other people. Sort of the motivation, we actually started the group more than a year ago at this point, but the motivation kind of comes from the sort of explosion of hardware solutions in this space, with different people making NPUs and DSPs and whatnot, and the way to compare them has sort of been lacking. So people will cite sort of random, we can operate at this energy point on this sort of general use case, but there's no standardization of like what model they're using, how they're using it, if they're including different stages of the pipeline. And so the goal we set out to do was create a ML benchmark for TinyML hardware, and like hardware specifically. And to do that, we sort of extended the ML Perf benchmark, which is just sort of a large industry academia collaboration around training and inference benchmarks for machine learning hardware. That's been going for a few years. This is sort of extending it down into the tiny realm. It also has the added benefit of doing some use case standardization. So if you're not a vendor who creates hardware, you can still use the models or the training scripts or whatnot as sort of like a popular workload that people are interested in, and do optimizations and test things there. We have over 200 members at this point, and a bunch of different people committed to submitting results in March. But we've sort of, through collaboration and through voting and getting the sort of industry perspective, we selected 4 different use case centric benchmarks. So we set out to try to select benchmarks that are relevant to industry use cases, and try to make them diverse across like sensor modalities and size and whatnot. So we have 2 that you guys should be very familiar, which is audio wake words and visual wake words. You've played around plenty with that. We also have, we actually just added tiny image classification, which is just using like CFAR10, the data set, and then sort of a novel one, which is time series anomaly detection, which is sort of different, but it takes a more of an industrial, like sort of factory setting, which is a sort of an exploding IoT market. And there's a lot of interest there. I'll go a bit more into anomaly detection because I think that's the only one you aren't all familiar with. We're using the MIMI dataset, which is just like actually kind of cool. So they take like slide rails, fans, different motor pumps and whatnot, and they essentially just run it and record the sound of it running, and then they intentionally damage it and then record the sound of that running. And the object is to be able to distinguish between normal operating sound and malfunction operating sound, but you're only allowed to train on normal operating sound because contextually, if you're designing one of these systems, you don't want to break your machinery just to learn how it runs. So you have to design a model around only being able to train on normal data. So it's kind of this unsupervised learning thing. The benchmark sort of adds an industrial focus and kind of an interesting fully connected autoencoder. But I won't get into too much detail about that. Version 1 is coming in March. We're going to have latency and energy metrics. Essentially, I mentioned all this just to say that a big push of our lab and of like the collaboration between VJ and Pete and whatnot has been to push standardization in TinyML and to build community. And I think benchmarks sometimes more than anything kind of build community around something. Competing vendors are coming together and agreeing begrudgingly on standard workloads and how to measure things. And sort of without these metrics and without these benchmarks, there's sort of no way to measure progress and no way to compare solutions. So you're sort of shooting in the dark. And that's sort of the sort of broad industry view on benchmarks. As Nat said, the profiling aspect is when you basically try the benchmark and you don't get a number you want and you have to figure out why. Yeah.
Also, one additional thing about TinyMLPerf, you can use the results from TinyMLPerf. They're going to be public. So if in the future you're working on a project, you can actually look at how each of these tasks performs on various pieces of hardware. And part of the reason why we compile this benchmark and we have a sort of a validation process for releasing results is that you can then compare the results against one another and use that to choose hardware that best suits your task. So it works both ways, where it's a good way for hardware vendors to compete and compare, and to release results. But it also means that when you're developing an application, you can do a better job of knowing what hardware to use for your application.
Yeah, and that was a huge reason why to pick relevant use cases for the benchmark, so that someone who's making the next Alexa smart speaker or whatever can look at our audio wake word benchmark and select hardware from there. So yeah, I think we can open it up to questions with Nat. If you have any questions about profiling, I know some, I think all of you should have some questions, because I think most of you are going to have to do some sort of profiling on device as the part of your final project, measuring in some way. So now's your access to an expert.
Everybody totally gets it, huh?
Yeah, perfect. Now, to say also, if you have any questions about TFLite Micro in general, or if you've run into any issues, any just overall questions about TinyML, yeah, as it pertains to TFLite Micro, I'm happy to answer or to pass those off to Pete or VJ, depending on what the question is. But yeah, it doesn't need to be necessarily specific to benchmarking or profiling.
Well, let me try to ask a question on behalf of some people who might have this question, which is, okay, so I've now decided that I want to do this profiling, benchmarking thing of my application. And I listen to this talk and I sort of understand that I need to do it. And I kind of get at a high level, like what I want to do. Like, what would you say are like the concrete, like first step or two that like everybody should make sure they set up to make sure that to like make it as easy as possible?
Yeah, that's a great question. I think the first stage that I would do is actually basically take one of the existing benchmarks in TFLite Micro and remove the whatever model it's using and drop your model in there in the place of that model. So just take like the keyword benchmark and replace it with your model and run that on your, run that on first just on x86 or whatever, your main development machine to see that it runs and that it, passes, that it doesn't crash. And then try to run that on your board and just see how long your application is taking to run. Because that's kind of how using this benchmarking library is going to be the first stage to kind of recognizing how your application performs as a whole. And then once you've done that, I think then it's a lot more up to kind of your requirements and what you want to, how you want to dig into it. But I would recommend kind of taking the approach of profiling for every operator in the graph and doing this by, I can sort of, if we go to the, this looks really simple. In reality, in a benchmark or in a test, a lot of times you will have created kind of a test of some sort that runs the model and compares your output. You have some pre-canned input, you have some output you're comparing against, just to make sure that it keeps running as you expected. Just make sure you provide this profiler when you create the interpreter in your test, and that should do this per op profiling for you. And that's kind of the second stage that I would do is to figure out what operators are bottlenecks for your model. Another thing you can try is just enabling, let's see, where did I put that? Yeah, so enabling this optimized kernel directory.
Context, you're not sharing anymore. I stole it from you and then stopped.
Okay.
Sorry.
All right, I will share again. So, am I sharing now?
Yep, all good.
Cool. All right, yeah, so, sorry, I was just talking about this. This is the per op profiling and just understanding, breaking down the graph based on each operator. That's kind of a good second stage. And this is what you should basically insert into your application, your test, or whatever you're using to run your model. And then another thing you can try is optimized kernel directory. And we have some examples of this in our documentation. If there are any issues with the documentation, please let us know. We've been updating a lot of things in the past couple months. So you may run into one or two things that don't quite match up. But basically providing this optimized kernel directory when you build using make is going to automatically bring in, it'll tell it where to bring in kernels that are specific to your board. And so trying this with the SymsysNN kernels, which are going to be under like TensorFlow Lite micro kernels SymsysNN, try that if you're developing on an ARM board in particular. And I think probably most of you are going to be. That's a good sort of first optimization to take and to see how much benefit that gives you. So that's like a broad. I don't know if all those stages are kind of clear. If you want me to dig a little bit deeper into any of them.
I will add to the end that for the Arduino libraries are I guess a bit different. So they already include the SymsysNN kernels, but if you end up using a different device, make sure that you add those. And I think it's actually a bit of an older version of TensorFlow, so it might not have some of these profiling tools. But I know there are some groups that are getting new boards, and just when people sort of investigate other, since you're all going to go into TinyML development in the future, you should all know this.
So are you using Arduino for your class projects right now?
Yeah. So we're using the Arduino Nano 33 cents BLE. Other words, I don't know. It's got a long name.
I think that's it.
Have you dug it all into compiling that library and using it sort of with custom versions, or not so much?
We've not. No, I think we're using built-in one. Yeah.
Okay. Yeah, I'm not sure if it's possible to. I don't know exactly what that API looks like, but I'm not sure if it's possible to enable exactly this. I know that it comes with SymSysNN by default, but if it's possible to do kind of the like per op profiling, that might be tricky with the Arduino library if you're not going to sort of recompile and use it separately.
Yeah, I
But
think it's
benchmarks
possible.
should be possible. Overall benchmarks should be.
And
Yeah.
I think for people that want to investigate some of these optimizations, you can probably make it work with platform IO and not including the sort of built-in Arduino library, and instead like using platform IO to compile that kind of stuff. The Arduino IDE doesn't sort of give you any freedom at all, but there are ways to just basically compile it for the MCU that we're using, which is a like Nordic MCU.
And there are also ways to create your own custom version of the Arduino library from like source code. So if anybody's interested in that, I'm happy to like help.
Yeah, I think that would be necessary if you do want to do this per op profiling, for example. The code change is pretty simple, but yeah, you'd have to create your own Arduino library basically.